Okay, now complexing agent. How do you get your complexing agent? Sure, you dissolve a chemical, right? Just that most complexing agents, the chemicals themselves are acid. They are acid. So now you have Ka versus the K formation kind of thing, such as that H2L is a weak acid, right? From the formula H2L, then you know it's a polyprotic acid. As it ionize or dissociate, then you get the products. And the product is still an acid, then you continue to ionize, then you get the L minus 2. L minus 2 is your complexing agent. Okay, so this is your complexing agent. Because you want to have the condition right for complexation, so this is the product you desire. The L minus 2 is the product you desire. Then how can you generate the L minus 2 in your mixture? Well, if you use acidic condition, if your solution is acidic, you dissolve H2L. Then the acid will push the equilibrium to the left, right? Because the original chemicals, they are acid, and therefore they will not ionize to give you the L, because of the proton in solution push it back. Notice the product is proton. So if you already have proton in solution, then there will be a resistance for more proton, and therefore will not ionize. On the other hand, if your solution is alkaline, so you have OH minus already in solution, then you dissolve those, then they will readily ionize to give proton to react with the OH minus. Okay, so the forward reaction will be favored under alkaline condition. So once you go forward, then you're going to generate the L2 minus simultaneously. Okay? So our future experiment will do a titration with EDTA. You all know EDTA is a complexing agent to complex with metal. Just that EDTA itself is also an acid. And the condition for the experiment with pH 10. So pH 10 is alkaline, right? So alkaline condition will generate the L minus for complexation. Okay, that's why. So that's why it's alkaline. Okay, so the H2L, back to this example. H2L into solution, then you're going to generate more or less of these. Okay, H2L, not ionized, ionized once, ionized twice. So all these quantities will be pH dependent. If that is highly acidic, then this guy is not going to be ionized. Okay, intermediate, then you ionize some. Highly alkaline, then you ionize, virtually total. Okay, so and your metal, for example, will need to complex with this species, but not that. So any questions with the background information? Okay. Now, another derivation. So, as we mentioned, we are interested in the complexing agent. So, the complexing agent, the quantity will be pH dependent, right? So we go to derive an expression of that dependency. Okay, so we are calculating for the L2 minus as a beta, as a fraction. So again, the definition. In a solution, you're going to have all those three species, right, of H2L. So the fraction for L2 minus will be expressed like the red outline, the red print, right? That represents the fraction. Now continue with the algebra. If you flip that over for convenience in a derivation, then it will be like that, and then like that. Now we are deriving for the pH dependency. So we want to change all that into H plus. Okay, so what we are looking at this here is going to relate with Ka, right? As you can see, this two contains protons. So we're going to substitute with the H plus somehow, okay? So now come with Ka. Ka is equal to this, right? So you know how to write the Ka. And then Ka2, so because it's polyprotic acid, right? So you get two Kas, and you can express like that. Okay, then you notice the fraction, the H2L there, and the HL is there. So you're going to rewrite expressing for the H2L, then rewrite it based on Ka1 will be like this. And then this one, based on Ka2, rewrite the equivalent is going to be like this. Okay, so these are the equivalents. Okay, then more equivalents because we want to see more protons in the formula, right? Okay, so the H2L now replace the HL minus because we don't like to keep the HL minus, but replace it, substitute by the H plus somewhere. Okay, so this becomes substituted, the Ka1, the H plus is right there, and this whole deal is HL minus. This whole deal HL minus. So substitute and rewrite, then you end up with that. So the picture is much simplified toward the route of seeing the pH alone. Okay? Okay, now we got this guy taken care of in this format. So now we can go back to the reciprocal, the beta. Okay, then for the H2L now is substituted by this guy right here. Okay, over the original L2 minus. Okay, so that becomes this, right? So the H plus dependency only. See, it becomes like this. Then doing similar substitution for HL, the HL right there. Okay, the HL equivalent is right there, and then over the original L2 minus, and it will be like this. So now you end up with a very useful formula. The fraction, reciprocal fraction, is equal to this. Notice, isn't it pH dependency? Right? Once you know the pH, then you know the proton concentration. Simply plug in, and then you know what the H2L is. So you look up the table for the Ka value like this. So the way to memorize this formula, if you want to memorize, which for calculations you simply use the formula, unless you are asked to derive the formula, right? With derivation, will give you confidence to use the formula, right? You know this is cool, this is what it is, and then you end up with this reciprocal beta is equal to 1, the first term, then plus 1 proton, 1 K. So it's a Ka2 to begin with. Okay, then the next one is the 2 proton, then of course that involves 2 Ks. So both Ka1 and Ka2 will be involved, okay, divided by